Hello, my name is Jordi Cenzano. I work at Meta since almost 5 years ago, and today I'm going to talk about media work week. So let's start. So this is the agenda for today. I'm going to try to explain what it is, why do we need it, or try to give you some reasons, and how it works, and finally we'll show some demos. So let's start. What is media work week? So media work week is it's a protocol that it's being developed in IETF. It's all open source. So if you go to this address, you have access to all documents and all the information that the work group, that the IETF work group produce. And a little bit, very brief history about MOQ, media work week. So this was born probably a couple of years ago when somebody, to be honest, I don't remember who, perhaps it was Luke from Twitch, but somebody realized that Rush developed a media protocol over quick, that Meta developed a media a protocol that sent media over quick that was called Rush, that we have it in production since 5 years ago right now, only for live ingest. And to be honest, it works, it outperforms RTMP. Not very difficult, but and then Twitch developed something similar on the Egre side that they call Warp, and Cisco developed something also similar, but their goal was video conferencing. So with those three, we thought, hey, we are building similar things in parallel. Perhaps we can sit down together and build something that can help the community, hopefully. So basically, and then it's when Alan Frindle, one of our co-chairs, started the Media over Quick IETF work group. So where Media over Quick sits on the protocol stack. So Media over Quick can run on top of raw quick or on top of web transport. And what can I send on top of Media over Quick? Whatever you want. Credit card numbers, video frames, audio frames. But to be honest, like its name says, it's designed to send media. But it's not only media, it's bytes, so you can put whatever you want. So here I put two examples, CMAF or a low overhead container that is also standardized in, there is an RFC in IETF. Okay, I think this is the main question that I'm going to try to give you some reasons about why do we need another media protocol. And this is the situation that we don't want to end up. So having another one, and then we have RTMP, ZigSee, whatever. So let me try to explain or give you those reasons, explain a story. So let's assume that you are a media engineer. I think it's a very good assumption. You go to work to a new job, and your manager says, hey, hello, welcome. So I have a job for you. You need to build a live streaming platform with the following requirements. It has to accept ultra low latency, like video conference low latency. Has to accept also the UGC use case, so a lot of contribution up to very high viewership, not as high as cricket, but let's say 1 million concurrent. And also it needs to work on browsers and applications and mobile applications. So good luck. That is a nice first day at job. But let's start thinking, obviously from the transport point of view, that this talk is about transport. What can we do to build that? So let's start from the very high level. We have a contribution, we have our viewers on the other side. So we need to send our stream to some cloud processor that does some processing, and finally deliver that to our viewers that are up to 1 million, probably globally distributed. So probably we will need some kind of distribution network. CDN. Protocols, what can we use? So ultra low latency, WebRTC, it's a very good fit. WIP, also RTC base, a good fit. RTMP, why not, it works. SRT, yes, RIST, ZigSee, whatever, all of this in contribution. And also we can do HTTP based contribution, why not? Distribution, we can also use WebRTC, so video conference use that, and they work quite well most of the time. And we can also do HTTP delivery, like all video platforms, almost all video platforms today. So there are two very clear groups here. The ones that are ideal for video conferencing, so ultra low latency, and others that are ideal for high viewership and high quality. Why is that? So this is a very simplistic diagram on how the videos and the protocols that are designed for video conferencing works. So basically they don't stop at anything. The data flow from there are proxies obviously, but the data flow from the producer to the viewer because they are designed to minimize the latency. But this is how the HTTP streaming or the HTTP live streaming works. The ingest usually seems quite similar, but then that processor in the middle, they aggregate all of these video and audio frames, they produce chunks, and eventually the player requests something that is called manifest. The manifest goes to the player reads the manifest, it requests those chunks because there are URLs in the manifest of those chunks, and then downloads those chunks. If I want to continue, this is live streaming, if I want to continue watching live streaming, I need to request another manifest. That manifest gets downloaded, gets processed, and then the next chunks comes. As you can see in this very, very simplistic block diagram, one of them is well designed for live streaming, the other is designed for cacheability or for scaling, let's say, not for ultra low latency. So let's try to answer these questions. Can I use video conferencing protocols for live streaming? Yeah. They will have very low latency, that's for sure. Quality, yeah, probably you can tune it, you can squeeze quite good quality, but when you go to scale, you will have very big problems, scaling to millions. And the opposite, can I use live streaming protocols for video conferencing? Okay, probably not, because the latency, you can, again, squeeze very low latencies from HTTP delivery using some tricks, chunk delivery and so on. But if you want to keep consistent ultra low latency, it's not possible. In a lab environment, yes, in the real world, not. So here is where we hope MOQ can help. So now that we know what is our ambition, because this is just an ambition today, so let's see how it works. How are we planning to make it work? Okay, so let me introduce first a couple of concepts. So quick streams. So as I said, this works on top of Quick. Quick provides some tools to the upper layers. One of them is quick streams. Another one is datagrams. In this case, I'm not going to talk with datagrams. In the working group, there is still some open debate if we need to use datagrams for MOQ. For now, the draft 01, it only talks about quick streams. So I'm going to focus on quick streams. So let me explain quick streams in just showing you an example. So this is quick streams are extremely cheap to open. So upper layers tells Quick, hey, I want to open first of all, our transport connection is established or a quick connection is established, and then I open a quick stream. And then I send frame video number 0, audio frame number 1, eventually I send video frame number 2 in this quick stream. Oh, some packets get lost, don't worry, the application does not do. So you don't need to care about that. Transport takes care of that for you, like TCP. So the quick transport will realize there is some packet loss, it will retry that frame number 2, and eventually it will send the frame number 3. Okay, what happened here? Exactly what we don't want to happen. Head of line blocking. Frame number 3, audio frame number 3, couldn't be delivered because we had a packet loss on time, because we had a packet loss of the video frame number 2, and we had to wait to recover that loss, and then audio number 3 was delivered. Let's assume this is a video conferencing that we want to prioritize audio over video. So, okay. Now what? Because this is exactly the same as TCP. Okay, let me introduce another concept. Multiple quick streams and send order. As I said, quick streams are extremely cheap to open. So why not open more than one? Quick allows you to do that perfectly. And then every quick stream that you open, it has a very, very simple prioritization scheme. One integer. If the integer is higher than other quick stream, those packets will be sent first. As easy as that. So let's see what we can do with those tools. Now we have video and audio, but look that the audio has a number 100. That is the send order. So send order is higher than 0, obviously. So now what happened here? Let me go back. So audio was sent first. And then, after that, when I had nothing to send, video was sent. Okay, nice. Next, video frame number 2 appears. I open another quick stream, and happens the same as it happened before. Packet loss. Oh, bad luck. Quick will take care of that for you. It will retry. But at that moment, the next audio packet arrived, 102. Higher send order. Audio was sent first. So what happened here? We just prioritized audio over video without doing anything at the application level. Just setting the right send orders. And quick transport did all of the heavy lifting for us. So this is what we try to do at MOQ. So take advantage of all the tooling that modern underlying network layers offer us to simplify the application layer. Okay, a couple of more abstractions. I think just 3 or 4 more, and very simple, I promise you. So let's see how we map media in this case, or video in this specific case, to MOQ abstractions. Super simple. I have a video track, so there is a MOQ abstraction that is called track. Okay, all my video is going to be a track. As easy as that. And then there is another abstraction that is group. Group is defined in MOQ as a joining point. So you can only start receiving data in the MOQ layer at the start of a group. This aligns perfectly with the video definition of a group of pictures. You can only start reproducing a video with a GOP starting with an IDR frame. Close GOP. Anyway, we map GOPs to groups. And finally, the latest abstraction in our, let's say, data model in a lot of quotes is object, and let's map object to frames. This is absolutely open. So your application.
A little bit more in.
Okay. So your application can do the mapping that you want. And now let me show you. And finally, let's map this to the network. We say that the tool that the network offer us is quick streams. So in this case, we map groups to a quick stream. So every group, I'm going to open a new quick stream and I'm going to send it over this new quick stream with the right send order. So in a live streaming case, probably I want the latest GOP created be higher priority than the older one, because I want to always be at the live edge, if this is what I want. So in this case, I'm going to put higher send orders in the newest groups. Okay, but I can do totally different for audio in exactly the same connection. And in this case, I'm doing it. So basically, in this case, the track is obviously the whole audio track, but I'm mapping every audio frame, so every 21 milliseconds, depending on the frequency sampling, but more or less any 21 milliseconds, into a group, and one object per group. And at every object or every group, I'm opening a new quick stream. Okay? And finally, this is the last definition. This is the easiest one. Roles. The one that produces media is the publisher. The one that receives the media is the subscriber. The relay can be both, obviously. And I can chain relays. And finally, the player is a subscriber. As easy as that. And this is how the information flows in MOQ. So very similar at what RTC does. But with an extremely important advantage. MOQ is cacheable. WebRTC, unless you implement it yourself, probably not. So that cacheability will give us the ability to scale up to millions. Okay, let's put some very quick examples. How a connection is established. First of all, if it's a browser, it's going to use WebTransfer because browsers does not have access to a quick player. If it's an app, you can choose WebTransfer or raw quick. And then, when the WebTransfer is established, I'm going to open a quick stream that we call control stream. That, remember, quick streams are ordered and delivery guaranteed, like TCP. And I'm going to send a message that, hey, set up. I'm publisher, I'm implementing publisher to subscriber, I'm implementing version whatever, this is draft 01, and I'm a publisher. And then, if I'm a subscriber, I'm going to reply, okay, good, I'm a subscriber, so you can start you can proceed the handshake. Okay, and then I'm a publisher, I want to publish something. I'm announcing that I have this track namespace, meta.com stream A, meeting A, whatever. And then if I'm able, or I want to receive that stream, I say, okay, good, send me the data. Sorry, good, you are okay to proceed. Sorry, I just forgot one step. And then the subscriber says, okay, this is a track namespace, but that track namespace can contain 1, 2, or 1,000 tracks. Now, I want to only receive the audio one, let's say. So now the subscriber sends to the publisher, okay, please give me your audio one of the stream that you already announced. And the subscriber, this is very important, sends this track ID. Okay, for you, audio 1 is going to be track ID 0. You will see that this is going to be used, this is just basically for compression, but this is going to be used in the next slide. So that's it. So all that we did in this handshake is say that the publisher wants to, the publisher will publish this stream, meta stream A audio 1, and this stream, that publisher will know this stream as track 0. All of this is, all this handshake, just to say that. There is some also conversations in the working group to simplify this. But anyway, this is what it is in the draft 01. And then, done. Publisher can start throwing objects in a data, in a quick stream, or in a multiple quick streams, that I strongly recommend you to do that. And now, thanks to all of that data, or basically thanks to the track ID, the subscriber will know. Sorry, oops, this is an old one that I forgot to. Okay, this I forgot to remove. So, and this is an object. This is what we put in the wire. This is the wire format. So 00 identifies an object. Track ID. So here, remember that an object can be as small as an audio frame. If we put a whole string identifying the track in an audio frame, it's going to be bigger, the string identifying that frame, than the audio data itself. So basically, that track ID is going to be 0, and then the group sequence is going to identify the group, object sequence, the object, send order. This is very interesting because this is what guarantees that all the MOQ hops will honor the send order that the publisher wants, unless you write some application that you want to rewrite it. But anyway, that's up to the application. If not, if you follow the protocol, the send order, all the hops are going to honor that send order. And finally, the audio bytes. Remember what I said, that track ID 0, the subscriber knows that that means meta.com stream A audio 1. Okay. This is just one slide. We have another RFC that we call catalog track inside MOQ. Because if you realize in the previous slide, the subscriber say, I want to subscribe to audio 1. But how the subscriber knows that that publisher has audio 1? We can send it that out of one. That is what I did in the demo that you will see after that. I didn't implement catalog yet. Or you can ask for the special catalog name track and say, hey, publisher, give me all you have. Or all I can see, all that you have that I can see. And then the subscriber chooses, okay, I want audio 1. So this is what, and also this catalog can provide any kind of metadata of those tracks. So this is something that is going to be used for more advanced applications like ad insertion, ABR, and so on. We need bitrate, we need friendly names, we need positions, timing, wall clock versus object number, and so on, so on. All of this is going to be in the catalog. Okay, that's all about catalog. Finally, demo. Can I see it? Of course. So let me just introduce what you are going to see. This is an implementation that I made, that I built for draft 01. So as you can see, very clear, I'm not a UI designer. But it works. So basically, this is a browser, a pure JavaScript implementation. And this is the web page that you will see. It requires, obviously, a relay to connect to, the URL relay, namespace, remember, track namespace, a track name, that this adds audio and video after this track name. You can see this information field here. max in-flight requests, so basically to limit the number of in-flight requests, and video encoding settings and encoding settings. And also it provides to the user some logs. So since this was more a testing exercise, I put a lot of timestamp logs to basically know what was happening there. And also every packet that I drop, there is a log or a line there, exactly the packet I drop or the frame I drop and the reason why I dropped it. Okay, this is for the encoder. Again, JavaScript application runs in the browser. For the player, same. JavaScript application runs in the browser, obviously in information that needs the MOQ relay to connect to, track name space, track name that needs to be the same as the publisher, and this is just information field that says that adds audio and video after that. Some very simplistic authentication that basically the secret needs to match with the secret of the publisher, as easy as that. And then very interesting data for latency. The minimum audio player buffer, the minimum amount of time of samples, but translated to time, that I need to start playing that stream. In this case, it's configured to 200 milliseconds, and the audio jitter buffer. Remember that I said that the quick streams are reliable and guaranteed delivery. Inside the quick stream, not between quick streams. So it's guaranteed, but it's not ordered guaranteed. So if I open two quick streams, nobody guarantees that if I send first a data in the quick stream 1 and then a data in a quick stream 2, the receiver can receive first the data in the quick stream 2. So if this happens, and this absolutely happens, then you need a jitter buffer. So in the receiver, so the relay is transparent. The relay just forwards objects. The relay doesn't care about the order, but obviously the video player cares a lot about the order. So basically you need to implement a receiver jitter that gets the data, reorders them before sending them to the decoder, and then sends that to the decoder. But also what can happen is that that data arrives out of your jitter buffer, so out of your latency budget. That can totally happen. So with the data that we put in MOQ, we can exactly detect when that gap happens and inform the decoder. So basically, do not break the decoder. So if there is an IDR frame that does not arrive, if I'm putting a frame in a quick stream, I can tell the decoder, or I can drop before sending the decoder the rest of dependent frames of the GOP and start with the next GOP. So basically, MOQ gives me that information of discontinuities in the stream to inform the upper layers on what to do. And also timestamp information, because the biggest pain of implementing this, it sounds weird, but I promise you, was the audio and video synchronization. Not the networking, it was the audio and video synchronization in a browser using web codecs. It's a thing. Okay, and then more timestamps and so on and so on. Okay, this is basically the quite accurate block diagram of what I implemented in the encoder. This is pure JavaScript. So basically, two web workers that captures media, audio and video. There is some audio and video alignment there. Very simple, very simple. And then another two web workers that does video encoder and audio encoder that uses web codecs. Then I used H.264 and Opus. Then I implemented the low overhead container. It's a very simple container. And finally, I send that data to another web worker that implements the web transport API in the browser. And that is the one that has the MOQ layer implemented. Relay. So relay is, again, it's very simple. So as I said, doing the handshake, the publisher says I want to publish this track. And then the relay receives also subscription from the other side that say, hey, I want to see this track. And finally, the publisher sends the data, and the relay has a in-memory table that knows that information that you have on the screen, so knows how to map that object to those subscribers, and it forwards and duplicates or replicates that object to all the subscribers that wants to see that object. The relay that I implemented is all in memory. Oops, sorry. The second, okay, yeah. Very important if you implement a relay and you care about latency. You need to implement read while write. Because if not, imagine that you put in one object you put a GOP. You can do that perfectly. If you don't implement read while write, you have to wait the whole GOP, so 2 seconds, to forward that object. That is a directly 2 seconds latency, and definitely you don't want that. So basically, remember that the structure of the object, with the first, I think, 6 or 7 bytes, you already know everything you need to know about the object. You can start forwarding bytes, and this is what this implements. And also, I'm not using this, I'm not using this for the demo, I'm using this for experimentation. I implemented a cache. Again, the demo is a VC demo or ultra low latency, it's just forwarding. You don't need to store anything in the relay. But if you want to start playing with VOD or rewind, then you need to store them. That's why I implemented it. And then the other side, the player. So it's basically what you saw in the encoder, but the reversed order. MOQ demaxer in a web worker using web transport APIs, the LOC MOQ parser, low overhead container demaxer, video digiter filter and audio digiter filter. This is the reason that I told you. We need to put the packets in order before send them, the information in order before send them to the decoders, audio and video decoders, and then a whole complexity to basically render audio in a browser and also try to do that aligned with the video. But this deserves 3 hours talk. Okay, finally, sorry for the delay, demo. So the demo was a video call. So basically I open an encoder and a player in each place. I was in San Francisco, that was 1 month ago. My wife was in Barcelona, in our house in Barcelona. So this is basically round trip time, and the relay was in Oregon. So from San Francisco to Oregon, 30 milliseconds round trip time. From my house in Barcelona to that same relay, 300 milliseconds. So this is the result. Oh, there is no audio. So she's my wife. She's in Spain, and I'm in San Francisco. So hello, Pilar.
Hi.
Okay, let's try. Pilar, please answer those questions as soon as possible. 2 plus 2.
4.
5 plus 5?
10.
10 plus 10?
20.
Perfect. Thank you very much for your help, Pilar. See you soon. Okay, that was a video call, a real one over internet. My connection is it's a gigabit connection, but I mean it's nothing special. So from San Francisco to Barcelona. And this is more scientific, in quotes, data that I collected. So basically, this resolution, 320 to 40, 30 frames per second, 500 kilobits, with a jitter buffer of 17 milliseconds starting at 10 milliseconds. From San Francisco to Frankfurt, the latency end-to-end, so San Francisco, Frankfurt, and back was 330 milliseconds, glass to glass. So measured by the typical and by this typical hassle, the photos and yeah. So again, this is what we saw in the video conference, but this is a more numerical proof. And finally, let me finish this talk with a hope. I don't know what the future of MOQ will be. I don't know. I think nobody knows. But definitely, I hope that if we are successful, that helps to improve and specifically simplify our current media ecosystem. I put some links here about other implementations. Mine, I will be open sourcing the player, encoder, and relay, but open sourcing at Meta, it's complex. Not complex, but requires some process. So I will be doing that probably before the end of the year, but here you can see other implementations. And that's all. Thanks a lot for listening.